Hi, I'm Ethan Burnett. I'm a PhD in Aerospace Engineering Sciences from the University of Colorado Boulder. In this presentation, I'm going to be talking about spacecraft relative motion dynamics and control using the fundamental solution constants. This is a promising new technique for formation flying that I investigated with my advisor, Dr. Hans-Peter Schaub, during my PhD at CU. It's well known that there are many choices of coordinates to use in formation flying. The local Cartesian and curvilinear coordinate representations are probably the most well known. Orbit element differences and ROEs parameterize some or all of the relative state in terms of integrals of motion. These have many convenient properties that might make them a favorable choice over local coordinate representations, but they're fundamentally rooted in Keplerian dynamics. So in this work, we ask, well, what about an approach that offers more general validity for diverse situations of interest? Can we find, for example, an approach that can be applied both in Earth orbits and in cislunar space? The approach that we developed is called the method of fundamental modal solutions. We use Lyapunov-Fouquet transformations to identify a favorable functional basis of relative motion in the vicinity of any periodic orbit. If you can compute the quasi-periodic Lyapunov-Perrin transformation, this method will be generally extended to motion in the vicinity of any quasi-periodic orbit. But this talk is focused just on the periodic case. So we have our local linearized dynamics with a periodic plant matrix. We compute our periodic reducing transformation and uncover a modal basis in a transformed linear time invariant space. And the modes in that space obey the principle of superposition, and transforming them back to X space via the LF transformation, we get our individual modes. So we can express any close proximity relative motion as a weighted sum of these carefully chosen modal motions. And the weights on these motions are our modal constants, and these act as our stationary coordinates, fulfilling the same role as orbit element differences. This approach has many benefits. First, it's computationally efficient with direct geometric insights. It's also directly applicable to many orbits. And lastly, it enables elegant control approaches. Analytically applying this methodology to the Keplerian relative motion problem of general eccentricity, we get this result that the relative motion can be decoupled into three planar modes, two decoupled 1D out-of-plane modes, and one planar drift mode, which is not shown here. And when we examine the relative motion modes themselves, we see that two of the three bounded planar modes are basic shapes, and the distorting effects of higher eccentricity are all mostly rolled into one fundamental solution, this third solution here. And over here on the right, I show an example of relative motion in black in terms of its constituent modes in colors. Then in these three plots below, I show how varying the scale of the three modal constants affects the type of motion I get. So this is a very convenient way to explore the relative motion problem because it would allow an astrodynamicist to quickly explore the possible types of motion and pick one that's useful. Over here, I give the new modal constants in terms of the spherical coordinate initial relative state conditions. So because these modal constants are integrals of motion for the unperturbed problem, we can express them in this way in terms of these initial conditions. And we can apply a similar procedure to relative motion in the circular restricted three-body problem. I'm going to skip through some of this for the sake of time. But basically, we end up with a double zero eigenvalue Jordan form in the reduced linear time invariant dynamics, which gives this secular drift mode if a period matching condition is violated. And this is fundamentally the same mechanism as what drives drift in the Closey-Wiltshire and Tschauner-Hempel problems. So it's a nice connection between the Keplerian relative motion problem and the circular restricted three-body problem. So this new approach would only be useful if it could account for off-nominal and perturbed cases. So we can use a variation of parameters approach to examine how the modal constants change for the case that the relative motion is perturbed. And we allow these constants to vary such that the weighted sum of the modes still correctly describes the relative position. So this is analogous to how the perturbed orbit elements describe satellite motion via the Gauss planetary equations. And over here, we show how the Keplerian modal constants slowly vary under the action of J2, for example. And as a result of this approach, in the absence of perturbations, we get this simple linear form relating a sequence of delta V's to the resulting changes in C space. There are some useful consequences of the previous control form for the unperturbed case. If we consider a set of all the reachable states with a certain amount of delta V, we can show that the set is compact and convex, and this allows us to adapt a control strategy from literature for such cases to do computationally efficient delta V optimal control with impulsive maneuvers. So here I have an example demonstrating that. We change from one relative orbit here in blue to another one, this one in orange, over the course of 2 chief orbits using 5 small maneuvers. And maneuvers are indicated on these plots of the relative state in C space and in the relative position plot by these vertical lines. And they're indicated by red dots in this 3D plot over here. A more interesting application of this modal control strategy is to apply it to the three-body problem. So for this example, I compute the L2 northern halo orbit family in the vicinity of the Moon, and I explore relative motion control in the vicinity of a stable halo orbit. So starting with this halo orbit, the modal decomposition shows that there is a trivial mode associated with the double unity eigenvalues of the monodromy matrix. And this mode is periodic in the CR3BP coordinates. Besides the associated drift mode, all other modes are composed of incommensurate frequencies, so they trace out these unintuitive shapes on long time spans. And this example control application over here, we start in the center subspace, which is bounded but not periodic, and we target bounded and periodic relative motion here in orange in the trivial mode. So this dashed line here gives the control trajectory. These little red dots give the control maneuvers, and we see that the target motion is achieved. Here is a sampling of other control examples from the CR3BP. You'll have to check out the paper to find out more about those. So in this work, we introduced this new method of using fundamental modal solutions in the close proximity satellite relative motion problem. And the approach we showed is valid for motion in the vicinity of any general periodic orbit, and via the variation of parameters approach, it's furthermore valid even if the periodicity is destroyed. So this technique allows for intuitive and numerically efficient exploration of relative motion. It also allows for computationally efficient control implementation using the modal constants. And we demonstrated this with applications to the Keplerian problem and to the circular restricted three-body problem. There are numerous opportunities for future work. We could explore computation of the modes in coordinates with superior linearization to extend the region of validity. We could develop the analogous application for motion in the vicinity of general quasi-periodic orbits. This would unlock extensions to other applications, such as relative motion in the full zonal problem, and the motion in the vicinity of quasi-periodic orbits in the restricted three-body problems, relevant to formation flying in cislunar space and in the vicinity of asteroids. That's the end of this talk. I'd be happy to answer any questions either in person at the conference or via email. You can reach me via email here, and also feel free to check out our lab website for some other work that might be of interest.